Right, so the last thing we need to do on my $50 3D printer, before I get the immense pleasure of trying to get it to actually print anything, is make our own custom flavor of the popular RAM shield to manage the 5 separate power supplies I'm using to power this machine. And who would be better suited to help us achieve this than PCBWay, who are sponsoring the channel again and supplying their high quality circuit boards for me to use. Now, when I originally planned this project, I did intend to just cobble together a makeshift shield on some strip board, which is still a valid solution, but considering I now have 5 separate voltage levels to work with, that would be a nightmare at the very least, not to mention kind of rude seeing as we do have a PCB manufacturer eager to help out. So before we unbox these boards, let's see what requirements I had and how I put it together. For the newcomers who may not have watched the entire series, I originally planned to use this ATX power supply for the entire printer, but that didn't work out with the heated bed, so I had to use this laptop power brick instead, at which point using this huge unwieldy hunk of metal just to power the hot end and a few motors was incredibly overkill, so I switched to using smaller wall wart style supplies that are way more common in e-waste than medium or big ones. This means each of them tends to a different part of the printer, so I made a little diagram to kind of get an idea of how this all comes together. And as you can see, the X and Y axis stepper motors get taken care of by this 24.5 volt supply with a rating of 0.8 amps. So each motor in theory has 400 milliamps at its disposal, which, after doing some experiments, I now know is way more than they need, and I actually had to turn the current limit on the stepper motor drivers all the way down to just 150 milliamps to avoid burning them out. The Z stepper motor eats kind of a lot of power, which is why it got an entire 12 volt 1 amp supply all to itself, and unsurprisingly, burning through that much power it also gets quite toasty, so I add an additional cooling fan here, which pushes this wall wart almost to capacity. The heated bed maxes out the 19.5 volt laptop power brick it also has all to itself. The hot end eats up a good portion of what the other 12 volt SMP, that's this one for reference, can deliver, leaving just about enough for 2 fans and potentially the Arduino Mega if I decide to power it from there in the future. For the time being though, I'll power it exclusively from the USB port, which should also help avoid glitches from interference. And lastly, the 28BYJ extruder got an entire own tiny 5 volt wall wart to itself. Now, my plan was to just download the official Ramps 1.4 files and modify it to suit my needs, but Ramps was created in Eagle and I'm using KiCad. And for some reason, I could not get KiCad to import the Eagle file, even though it should theoretically be possible. It just left me hanging with an error message. And since I don't like Autodesk's cutthroat subscription model equivalent to Adobe with its Photoshop, I obviously wasn't going to make an Autodesk account and download their software just to have my files stuck in their cloud in a proprietary format afterward. So the only solution was to recreate the entire schematic from scratch in KiCad, which ended up only taking a few hours and wasn't a huge deal given I would have had to do the board design from scratch anyway. As you can see, it's pretty much a 1-to-1 copy of the Ramps 1.4, except for the power section where I added 4 additional inputs with their respective fuses and filtering. I really don't know why I even added those fuses because, as you saw earlier, those power supplies are almost maxed out to begin with, and fuses generally needing to be oversized by about 33%, most switch mode power supplies are going to shut down before ever delivering a current 30% higher than what they are rated for. So the likelihood of these fuses ever blowing is close to 0. I also added those reverse polarity protection diodes for good measure, even though all my power supplies will be connected via barrel jacks, so accidentally inverting polarity wouldn't even be possible. But I added them anyway because why not? I have tons of random salvage diodes laying around that I can put in, and maybe they can filter some reverse current spikes or look pretty. The only other thing I did differently than the Ramps shield was the MOSFETs. Ramps uses 3 identical 60 volt 50 amp MOSFETs for the heated bed, hot end, and part cooling fan. Since a 50 amp MOSFET is incredibly overkill for switching a 60 milliamp fan, I took the liberty and downgraded it to a small TPC 8073, which can switch only 18 amperes. Likewise, the hot end, which only needs 3.4 amps, got an STD 1703 I had laying around. Finding a MOSFET for the heated bed turned out a lot more difficult though, because my heated bed runs on 19.5 volts, and while I have some IRF 540 and 640s, those have a pretty high on-state resistance, and with my heated bed just barely powerful enough to reach 100C, I want to take as little power away from it by heating MOSFETs as possible. Unfortunately, all the low resistance MOSFETs I had desoldered from various PC motherboards also have a very low voltage rating of just 20 volts, which of course wouldn't go down very well with my 19.5 volt supply voltage. I was incredibly lucky to find some Infineon 30 volt MOSFETs with a low on-state resistance and 50 amp rating on an old motherboard I hadn't desoldered yet, so I took those out, and while I was at it, I also removed screw terminals for the heated bed and hot end from an old automatic gate opener. Now, the 30 volt MOSFET isn't ideal given there's not all that much headroom from 19.5 to 30 volts, but it's the best I currently have and it should do the trick. Now, laying out the PCB was kind of a nightmare, and I started to regret including all those unnecessary components and empty footprints for potential future use. Turns out, with RAMS 1.4, they did a really good job squeezing stepper motor drivers, capacitors, fuses, and MOSFETs on a board barely larger than the Arduino Mega itself. Since I used so many clunky through-hole components, there was no way to fit them on, so my shield comically turned out quite a bit larger than the Arduino it sits on. You can see here's the outline, and that's how far my board protrudes. The real problem with putting so many components outside the perimeter of the Mega is that I cannot have any current carrying tracks crossing those rows of header pins, as there's simply not enough space to sneak them through. So all high current stuff had to go around this open side here where the Arduino has its power management too, but because all my barrel jacks must go on the one side of the board where the USB port of the Arduino is, my hot end and bed MOSFETs on the outputs had to be shoved back here. Granted, I'm pretty bad at routing circuit board traces in general, but all in all, I probably would have been better off just building an entire controller board from scratch using just the Atmega 2560 chip. But then I would have had to deal with the footprint directly, and the last time I tried to do that, it didn't go so well. This is what the end result looks like. Most of the connectors and fuses are missing here in CAD, plus a few of the footprints aren't actually going to be populated in real life since they're just optional, like this 5th stepper motor driver. I only have 4 motors, so why would I waste components for a 5th? Just like with those servo, auxiliary, and serial connectors, they are all gonna stay empty. The underside of the board is also empty except for the pin headers that plug into the Arduino. Either way, that is pretty much all I have to say about the design step. If anyone wants to make their own RAMS knockoff in KiCad, I'm going to make the files for this available in the description. That way you don't need to bother redrawing the entire schematic. Anyway, it's finally time to unbox these boards. I probably trashed my viewer attention again with all the blabber. Leave a comment if you didn't skip. This time I actually went for a different color than yellow because I was kinda getting fed up with it. Looks like we got another pen, and the stickers now have an outline rather than being rectangles. And here we have the boards. Yes, they are red. It's also part of my brand coloring. Honestly, these guys are spoiling me. Would I even still bother etching or CNC routing my own PCBs if they weren't sponsoring this? I don't really think so. These are way better quality than what many mass-produced products come with. I just hope I didn't make any mistakes on one of the many custom footprints I had to design. Imagine the shield not actually fitting the Arduino. That would be a disaster. And as you can see on the back, I also managed to come up with a ridiculous name for this 3D printer. It's going to be called Chronicmechatronic because it's the dinosaur of my 3D printing age and kind of reminds me of my very first table saw, which I unfortunately don't have any pictures of to show you. But when I designed this machine over 2 years ago, I knew nothing about 3D printing whatsoever, so I learned a lot building this, and consequently the design is pretty outdated already, which fits the name dinosaur even better. I know, my engineering is the worst of both worlds, NASA's sluggishness and SpaceX's adventurousness combined. But hey, we're not building rockets here. At least not yet. But let's not get distracted and start assembling this Ram's Shield Chronic Mechatronic edition. I went ahead and made a bill of materials, even though I already have all the components I need here. I generally gather the components while designing the PCB. Goes without saying that all these components were scavenged from e-waste and are about to start their second lease of life. I only had to subsidize a bunch of new header pins and sockets, since those are rarely used in consumer electronics. There is one component missing, however, and that's the barrel jack on the Arduino Mega. I need to desolder it because A, having a jack that should not be plugged in right next to several that should be plugged in would be way too confusing, and B, it'll be of more use on my Shield than on the Mega. Also, as opposed to the previous boards I made, this time I'm gonna give reflow soldering a try. I picked up some solder paste and one of those PTC hot plates from China and mounted it on a makeshift base so I could use it. Before the comments pour in, I know this is a horrible design. It gives off a faint wisp of smoldering cork, and the hot glue I use for cable management underneath, surprise surprise, starts to melt. But it'll do for this video. I guess I should finally shut up now and start placing components. Nah, sorry, not done talking yet. It's worth mentioning the reason I'm not using a stencil to apply the paste is that only about half of the board is going to be populated. For example, the big SMD resistor footprints you see, those are actually for 0-ohm links that can be put on to configure the board for certain use cases. And putting a link on all of them might blow something up, so yeah, better not do that. The MOSFET's got a heat-sinking copper pad. I have no idea how hot those get and if it'll be sufficient cooling, but I guess I'm gonna find out soon enough. And yeah, I'm definitely using way too much solder paste, especially here, but don't worry, I'm about to learn that the hard way. And that is it, ready to reflow. Now this is where things really went south, pretty much all the way to Antarctica. You see, I'm really trying to get some nice macro shots here, despite the fact that the lamp blocks my view of the camera screen, and the camera prevents me from seeing what's going on the circuit board, because I'm using a smartphone to film my videos, and the macro lens has a really short focal length, meaning I have to get extremely close to the hot plate. At this point I realized things had already molten into a disaster over to the left, and I really wanted to die. Look at that resistor totally upended. And poking those components around to seat them correctly while single-handedly holding a camera that doesn't have image stabilization in the other just doesn't work. Now back in the tripod after showing you the worst footage you've probably ever seen on YouTube, let's see if we can fix this despite having used 3 times the necessary amount of solder paste. I also have the feeling my hot plate may be way too hot because you see the solder resist darken, which I definitely don't think is supposed to happen. Either way, it's finally time to reflow the big boy. Look at how it floats on a pool of excess solder. And inhaling a lungful of fumes is always a great option. Please do not tell me what toxic chemicals there might be in the flux of that solder paste. With the reflow disaster behind me, I can clean up the scene, wiping away the solder paste that spread across half the PCB with a cotton bud and isopropyl alcohol. I'm using the slightly concave tip of my soldering iron to reflow every solder joint because it does a great job at wicking away excess solder and collecting those tiny droplets that are still scattered around the perimeter of components. A few more Q-tips and a lot of isopropyl alcohol later, I can finally move on to the through-hole components. For those, I have to use a different soldering iron because that solder is lead-free, and neither my trusty old light blue soldering iron nor my 30-watt DIY soldering station get hot enough to melt the solder and heat a pad simultaneously. And even the one I'm using now doesn't have enough oomph to deal with pads connected to the ground plane without me feeding in some lead solder to lower the melting point. The LEDs are getting a little nylon spacer to raise them off the PCB a little bit and make them more visible amongst the other components. I actually color-coded them, so with the beta output a red LED lights up, the hot end got a yellow one, and the cooling fan blue. I thought that made sense. But back to the topic of lead-free solder, let me tell you, I hate this stuff. It just doesn't work, and so far I haven't managed to get a hold of proper lead-based stuff because everywhere it's sold it's incorrectly labeled and or at least 3 times as expensive. So now I only have a little bit left which I can't expend the majority of for this one board. I've actually come to a point where I would even be willing to spend $10 to get a roll of decent solder, provided I could be sure I wasn't scammed by a false listing. So I guess I'll eventually be forced to go lead-free against my will. I mean, regulations for toxic chemicals are great and all, but pure tin just doesn't work. Fortunately, I really like SMD technique, so the more I lean into reflow, the less I'll have to deal with stupid heat-sucking ground pads. The solder paste I got has bismuth in it, and seems to flow really well even with little heat from the soldering iron as long as there is flux surrounding it. Yeah, it's way more expensive on a per weight basis, but you also need way less, as I just discovered spectacularly. Now for the screw terminals, I have to use some of my precious remaining lead solder, as the pads and traces are so substantial for the high current, I'll never manage to heat this up to lead-free temperatures. Look at how much better it wets the surfaces. So that's it, pretty much done. And you might have noticed I have one barrel jack left over. That one's supposed to go here for the 19.5 volt heated bed, but I realized when the shield plugs into the Arduino, the pins short out against the metal shell of the USB port because the height of the header pins leaves no gap. I guess not making any mistakes in PCB design is not an option. But I can fix this rather easily by trimming the connector pins flush with the circuit board and using solder sparingly so it doesn't bead on top of the pads. And although I generally don't like plated through holes, they are really saving the day here. Then I can put 2 layers of Kapton tape over it, and voila! Disaster averted! Given the size difference of those boards, I'd say it's more of a PCB with an Arduino stuck to it than it is an Arduino with a shield on top. Now I can mount it to the back of the filament spool holder and start hooking up all the wires. But first I need to attach the 24 volt power supply, which goes right underneath here. It has a hook thingy on one side that it used to be attached with, so I simply made a corresponding negative out of wood for it to slide into. This gets screwed to my filament holder, and then the power supply can be slid in and screwed down just like it originally was intended to. To attach the electronics, I made the exact kind of tray you normally see people 3D print out of wood. They both go on here, and it gets screwed to the machine. Actually, the order here was slightly wrong. First the tray gets screwed to the machine, then the Arduino gets screwed to the tray, and finally the shield gets plugged onto the Arduino and also gets screwed to the tray. And now I can start plugging things in. The extruder stepper motor, the Z-axis fan, the 24 volts. Oops, that wasn't planned. How on earth am I supposed to plug that in? Alright, I fixed it and finished the wiring off camera since this video is getting kinda long and you've seen enough boring soldering for the day. So this is what it looks like, and in case you wondered why I only populated 2 motor slots, it's because the other 2 are outsourced, so to speak, to my unipolar stepper motor drivers for the Z-axis and extruder motors. And I simply ran signal and power lines to the corresponding footprints on the PCB. Only the X and Y-axis motors get an A4988. Speaking of the A4988, I still need to stick those on, and even before that, I need to set my micro-stepping jumpers, because this is in fact RAMPS 1.4, so almost everything, including most of the documentation, should be applicable here as well. I'm gonna set them to quarter steps because when testing those motors on 24 volts, I noticed not only are they able to go much faster, but micro-stepping works better too. So where before the maximum resolution I could get was half steps, I now seem to get smoother operation up to quarter step mode. Yup. And that is the Chronic Printosaur technically complete. Exceptionally, we're not gonna test it in this episode because I haven't got a damn clue what I'm doing. I have never worked with 3D printers before, so this will take a bunch of time. By the way, I compiled and installed Marlin on the Arduino before even starting this video, so that's at least something I don't need to do anymore, but there is still a ton of things I need to calibrate, like I have no idea what the maximum feed rate for the extruder is, and so forth. I'm gonna do all these things mostly off camera, and in the next episode, we'll print the first Benchy, however good or bad that may turn out. Huge thank you to PCBWay for supporting this project and sending out these awesome PCBs. I don't even want to think about the headache trying to squeeze all of this onto a piece of single-sided perf board would have led to. Also, genuine thank you to all my patrons. It truly goes a long way towards making this channel a sustainable thing without going overly salesy. I really love making this content for you guys. I don't plan on stopping, so being able to call this my job would be a dream of mine, and I am grateful for all the support. And with that said, I'm gonna leave you guys. The next episode is unfortunately not going to be the next video. Sorry, there will be something we haven't yet done on this channel in between. I hope you enjoyed, and I'll see you soon. Bye bye!